Thank you. So, since it's my first Microlensing conference, I guess I'll just introduce myself. I'm Mauritz. I'm now at the University of Warsaw. I just started my PhD under the supervision of Wicker, who unfortunately can't be here this year. And I'm also a member of the Gaia Consortium, so of Gaia DR3, the variability processing group led by Laurent Ayer in Geneva. And we've been talking about some great upcoming missions in the past few days, and so I would like to talk a little bit about, as Sophia has also talked about, a mission which has recently come to an end, or is currently in its last or in its last ending phase, which is Gaia. And so about the Gaia Space mission, just briefly, it was launched in 2013. It is not specifically a microlensing mission, but rather an all-sky mission, which is scanning the entire night sky with a cadence of about 30 days. And the mission, as you can see, just recently ended in 2025. And I'm very lucky that I had my talk on the last day, because here we can actually see observations of the Gaia Space Telescope taken by a 50-centimeter telescope in Poland. So what Gaia is doing at the moment is it finished its scientific observations about 2 weeks ago, and now for some final tests, for which it's using its final piece or bits of fuel, it has been tilted so that it increases in magnitude as it's reflecting more light from the sun, and it's actually at about 15 mag at the moment. And so, seeing these beautiful images of the telescope, I proposed a new patch for the mission, which unfortunately was not received very well, but we'll stick to the old patch. And so on the right, we can see Gaia telescope, which has a large sun shield of about 15 meters diameter, and it actually has two observing telescopes, so to speak. So it's observing with two inputs, which are separated by about 100 degrees, and in doing so, it creates the most precise 3D map of the Milky Way, or that was at least its goal, and if we may say so, I think it has achieved that. And in doing so, it measures positions, distances, and motions of over 1 billion sources, which are published in individual data releases. So the next data release is DR4, which is expected to come end 2026. And what's impressive about Gaia is we achieve lots of different data. So we get photometric data, astrometric data, and spectroscopic data. These are just 3 of the data sources which are very important for us in the microlensing community. And so looking at the Gaia focal plane, which has a size of about 1 meter by 0.5 meter, so a very, very large group of CCDs. And what happens when Gaia is scanning the sky is that moving from left to right, a star enters the CCDs in the sky mapper and then moves across the astrometric field before it passes through 2 spectrographs, so the BP, which is the blue photometer, and the RP, which is the red photometer. And if it's bright enough, it also actually enters the high resolution spectrograph, which is represented by the green squares on the right. And so the next data release, as I mentioned, is Gaia DR4, which will have full astrometric, photometric, and radial velocity catalogs. This is based on the first 5.5 years of the mission. So although we just finished over 10 years of mission, the data which is coming is still only from the first 5.5. So DR5 and DR6 will be an even bigger treasure chest. And what we, as the microlensing group from Wicker, are trying to do, also with many people here sitting in the crowd, is to produce another catalog of these events, like was available or is available in DR3, and included in these events is this not only photometric modeling of parallax, but also to include astrometric modeling, and then also to look at individual events. And I think the biggest take-home message for the microlensing community about Gaia DR3 is that we will have photometric, astrometric, and spectroscopic data for these events which were observed or have not been found yet, with a cadence of about 30 days between 2014 and 2019. And one of the things which instantly pops up is, well, we only have a cadence of 30 days. So it's quite hard to fit microlensing, whether astrometrically or photometrically. And for this, Wukash coordinates the BH-TOM, the Black Hole Target Observation Manager portal, which is based on the TOM platform. And the goal of this is to coordinate a network of telescopes, manage astronomical observations, and to process the data obtained from these observations. And this means if you have a telescope, or your university or something has a telescope, you're more than welcome to sign up. Or if you're an observer and you want data for these events, or doesn't have to be microlensing events, any time domain astronomy, you're more than welcome to sign up. And in practice, what this looks like is that we go from microlensing events which have G-band data like this to microlensing events which have data observed from many different observatories collected. So here we can see we have ZTF or even WISE or Atlas data combined with observation from smaller telescopes, be it 30 centimeter up to large telescopes. So it's a great way to connect these communities and also combine data which otherwise might be inaccessible for many people, and which is very useful for analyzing our events. So just to have a brief look at what we can expect in DR4 is, here's an example of Gaia DR3 ULAN 001, which was published by Jablonska, also part of Wicker's group in 2022. And not to get too exact about this event because it's I was not involved in the event, but I think it's a great example to show the quality of the data that Gaia will have, even if we only look at this data, so not using follow-up data. Photometrically, we're able to fit a photometric point source model, which can give us the Einstein parallax or the Microlensing parallax, and in theory could also give us information about the theta E, which in this case is not possible since we don't observe finite Swiss effects. But by combining this with astrometry, we're actually able to, in theory, produce a mass determination of this object. Obviously, the data in this astrometric event is simulated, so I'll show you some data I simulated with Astromet to show the power that we have, and to over-exaggerate the estimate we can get on the lens mass, but in theory, it's possible. So here I have some simulated data from the observed event. So this is what we would see from Gaia. And this is very simplified. We're not considering scan angles or no errors involved. And so by fitting this astrometric light curve, we can actually see the microlensing event. By determining theta E, we can reduce it down to the source path, and this would give us a direct mass measurement. So now to move on to a little bit of the work I've been doing and to just show you some of the power Gaia has from simple photometric analyses. I'm going to be talking about 18 microlensing events which were alerted by Gaia, which I analyzed. And so these events were alerted by the Gaia Science Alerts campaign run by Hotchkiss in Cambridge. And the events are marked here on the right by the red dots, where the blue dots represent all the microlensing exoplanets. So what this shows is great power Gaia has in finding microlensing events which are far away from the bulge. So we're able to probe the entire galactic plane or even the halo. And so what I did is I fit these microlensing models using the Pylema software, and by using wave sampling from synthetic microlensing events obtained from the Besançon model, we're able to produce estimates on the lens mass. And this is work that I did during my master thesis, which I did with Markus Hundertmark and Joachim Bamskans in Heidelberg. And so here are some of the results from these 18 events. We find 8 dark lens candidates, ranging widely in the constraints we can set on lens mass. So for example, if we do not have Gaia data, which is useful because it's a blended source, or if we don't have tight constraints on the distances or on the parallax from the event, we have large error bars for the distance, for example, even for the mass measurements. But as a holistic view, we can see that we're able to probe a large population of sources with this method. And to look at it in the night sky, again, to show how we're able to look at events around the entire Milky Way. Here we can see for each event, the sources marked in red and the lenses determined marked in blue, with a wide range of precision for the distances determined. But also for some events, we can see we're actually very good at constraining the positions of sources and lenses through this method. And so just to briefly summarize, data release 4 from Gaia is soon to come, and what we are currently working on. And the main takeaway from this is that we will have time-domain data for both photometry, astrometry, and actually also spectroscopy in low-resolution BP and RP bands. And as I'm in the black hole time slot of this conference, just a little outlook on the ideas we have concerning black holes is we have hundreds of microlensing events that we have found or are finding in this data. About 100, we could find astrometric signals, which we are including in the models. So we are expecting or hoping that there should be some black holes hidden in this, which is the work that I'm doing. Thank you.
Just a curiosity, in your plot, there were two binaries with very low mass, 10 to minus 2. So have you investigated?
Yes, so this is actually an external candidate, but it's also worked on by different groups, so it's not my proprietary
This event is the total mass of the lens or the mass of the secondary object?
From the secondary object. So yeah, so for both of them, the companions are a little bit higher, so the mass is about I think a half solar mass. Yeah.
For the sample, did you do any selection cuts on TE or anything else?
For the sample events? No, so they were actually rather randomly chosen. So I looked at many events and then just looked at some which actually produced results which I could analyze. And since it was my master thesis, I was looking to more learn the methods than really find specific events. Yeah. And so yeah, we looked for a wide variety of binary lenses, point source lenses, point sources for lenses, and like parallax, no parallax, finite source. So just to try and cover a wide range of events in a large area of the sky.
I'm curious about the uncertain candidate. Does it have like a near finite inerrancy, or what's the reason for the uncertainty?
Yeah, good question. So for the uncertain candidate, it's that there is rather large blending, which on the extremes could be due to the mass, but it's not like 100%. So I put it as uncertain instead of labeling as a clear black hole candidate, which has a blending star, which is unlikely. So it's most probably a high mass main sequence star, but uncertain because the blend doesn't absolutely fit.
Okay, thank you.
Then we plan to publish these results.
So for individual events, we're definitely going to look in the DR4 data, also looking at the astrometry. So for these events, to constrain the parameters more, but nothing concrete in the pipeline.